All right, we are in section 4.4. We are talking about L'Hopital's rule, and this is a really handy rule to know when it comes to limits. If you're in indeterminate form, that is 0 over 0 or infinity over infinity, you can rewrite this limit by taking the derivative of the top divided by the derivative of the bottom. Now, of course, in using L'Hopital's rule, you have to have a quotient. Okay, now there is no quotient rule, but you have to have a quotient to use L'Hopital's rule. Now we've looked at several examples here, now sometimes there's going to be some limit calculations, but you don't initially have a quotient. Okay, but you're still going to need to use L'Hopital's rule. So let's take a look at this example here. You got the limit as x approaches 0 from the right of x times the ln of x. Okay, now the fact that I'm approaching from the right is because of this ln of x here. I know I can't take log of 0, I can't take log of a negative. Okay, I can only have positive overall values going inside of a logarithm. Now the direction is a necessary thing here, okay, because I don't have a graph on either side of the of a logarithmic curve there. Now, if I were to make a direct substitution, I know 0 times any number is 0, but see, the limit as x approaches 0 from the right of the ln of x, that would be negative infinity. Okay, here's a quick graph of the y equal the ln of x. Now, if I'm approaching 0 from the right, the y values are growing without a bound in the negative direction. Infinity is not a number. Okay, so I can't just say that the answer is 0 or anything, okay? Because infinity is not a number. So I would want to rewrite the inside here as a quotient. X is the same as 1 divided by 1 over x, right? Because if I flip the denominator and multiply, I'll get back to the previous line. Now, I've written it like this so that I can think about if I'm in indeterminate form next. Okay, the limit as x approaches 0 of the ln of x, I just said that that was negative infinity. Okay, the limit as x approaches 0 of 1 over x, well, here's the graph of 1 over x. If you're approaching 0 from the right, the y values are growing without a bound, right? So you get infinity. We are in indeterminate form then, right? Negative infinity over infinity. So I can use L'Hopital's rule. Remember, the h just means that you're going to apply L'Hopital's rule at that part of the calculation there. So you got the limit as the limit as x approaches 0 from the right of the derivative of the top, that's 1 over x, divided by the derivative of the bottom, 1 over x, that's the same as x to the negative 1, and you can use the power rule then on that. Negative x to the negative second, or negative 1 over x squared in fractional form. And since you're dividing by a fraction, you can flip the denominator and multiply. Negative x squared divided by x is negative x, and now there's no problem with plugging in 0. We get 0 as the answer there. Okay, let's take a look at a few more examples here where we have to rewrite the function inside the limit as a quotient. Okay, here's another example. You got the limit as x approaches infinity of x times tangent of 1 over x. The limit as x approaches infinity of 1 over x, that's 0. And tangent of 0 is 0. 0 times any number is 0, but see, here's another problem. Infinity is not a number. So I wouldn't just conclude that the answer is 0. If I were to say 0, I'd get a wrong answer, by the way. Okay, so I wouldn't want to think of the problem like that. Instead, I want to rewrite x is the same as 1 divided by 1 over x, and I've now got a quotient. So maybe I want to see if I'm in indeterminate form now. Well, the limit as x approaches infinity of 1 over x, that's 0. Tangent of 0 is 0. So yeah, you're in indeterminate form, 0 over 0, which means that you can use L'Hopital's rule. Okay, so I'm going to go ahead and do that here on the next line. We got the limit as x approaches infinity of the derivative of the top divided by the derivative of the bottom. Okay, the derivative of the bottom would be negative 1 over x squared. The derivative of the top, that'd be a chain rule, we're going to have secant squared of 1 over x times the derivative of 1 over x. That's negative 1 over x squared. The negative 1 over x squareds are going to cancel there. And the limit as x approaches infinity of secant squared of 1 over x. Well, the limit as x approaches infinity of 1 over x, that's 0. Secant of 0 is 1, right? Because cosine of 0 is 1. Secant of 0 would be the same as 1 over cosine of 0. 1 over 1 is 1. Yeah, so if I would have said 0 here, it would have been wrong, right? Okay, here's another example about the limit as x approaches 0 from the right of sine x times the ln of x. Well, sine of 0 is 0, but the ln of 0 is undefined, right? I can't take ln of 0 or ln of a negative. So I wouldn't just conclude that the answer is 0, although in this problem it is. Instead, I'd want to rewrite sine x times the ln of x as a quotient. Sine x is the same as 1 over cosecant x. And, okay, am I in indeterminate form now? Well, let's see here. So cosecant of 0 is undefined. There'd be an asymptote there. Since sine of 0 is 0, and cosecant of x is the reciprocal of sine x, you'd have an asymptote there at x equals 0. Okay, and of course there's a vertical asymptote at x equals 0 on the graph of y equal to ln of x. So yeah, we're going to be in indeterminate form here. We're in the form negative infinity over infinity, and so I can use L'Hopital's rule. Okay, you got the limit as x approaches 0 of the derivative of the top, that'd be 1 over x. The derivative of the bottom, that'd be negative cosecant x cotangent x. And cosecant x, 1 over cosecant x, that's the same as sine x. 1 over cotangent x, that's the same as tangent x. The negative can be brought outside the limit. And now how about the limit as x approaches 0 from the right of sine of x over x? Now this is actually a limit that we have already seen way back in section 3.3 when we were talking about the derivatives of the trig functions. We did this limit. That was the very first problem I had done in that section. And if you were to flip back in your notes, the way that we did the problem was kind of involved. It took like a half page of work. You know, that's one way that we could do the problem. Now, we were kind of limited with the information at that point, but now that we know more information and we can use L'Hopital's rule here, we can get the result in one step. So I am in indeterminate form. Sine of 0 is 0. You can apply L'Hopital's rule, and now there's no problem with plugging in 0. Right? The answer is 1. Okay, way easier than what we had done before. Okay, so in this problem, the limit as x approaches 0 from the right is of sine of x over x. That's 1. The limit as x approaches 0 from the right of tangent x. That'd be 0. Tangent of 0 is 0. Right? The direction is not relevant, and in plugging that number in, so we end up getting 0 there. Now, by the way, the direction is relevant in the earlier parts. You know, make sure that you have that written, because if I had the limit as x approaches 0 of the ln of x, that's not defined. Okay? The limit as x approaches 0 from the right of the ln of x, that's negative infinity. Okay, something that does not exist and negative infinity, those are two different results. Okay? So the direction does matter, right? Here's another example. Let's take a look at the limit as x approaches pi over 2 from the left of secant x minus tangent x. Now, if I were to split this into two limits, that would be okay, but I wouldn't be able to get further from that, because secant of pi over 2 is undefined, tangent of pi over 2 is also undefined. Since in both of these you'd have cosine of x in the denominator, and cosine pi over 2 is 0. We know we can't divide by 0. So I wouldn't want to think of the problem like that, where I just, use my limit law. Limit of a difference is the difference in the limits. That wouldn't help me in this problem. Instead, let's go ahead and apply our quotient identities. Secant x is the same as 1 over cosine x. Tangent x, that's the same as sine x over cosine x. And I can get a single fraction out of that. I'm creating a quotient. And can I use L'Hopital's rule now? Well, cosine of pi over 2, that's 0. Sine of pi over 2 is 1. 1 minus 1 is 0. And yeah, so I'm in an indeterminate form. I can use L'Hopital's rule. And I'm applying that now. We got the limit as x approaches pi over 2 from the left of the derivative of the top, that'd be negative cosine x. Derivative down under, that's negative sine x. Okay, now there's no problem with plugging in pi over 2. Sine pi over 2 is 1. Cosine pi over 2 is 0. 0 over 1 is 0. Okay, the next thing that we'll have to look at here in this section, the last thing also, is what's called indeterminate powers. Okay, if you have the limit as x approaches a of f of x to the power g of x, and you can't make a direct substitution for the a value, you'd want to maybe consider if you're in an indeterminate power form. All right, item 1, if the limit as x approaches a of f of x is 0 and the limit as x approaches a of g of x is 0, then you're in indeterminate power form. You'd be in the type 0 to the 0 power. Item 2, if the limit as x approaches a of f of x is infinity and the limit as x approaches a of g of x is 0, you're in an indeterminate power type. That'd be the type of infinity to the 0 power. Item 3, if you have the limit as x approaches a of f of x equal 1 and the limit as x approaches a of g of x equal infinity or negative infinity, then you'd be in an indeterminate power form where you're 1 to the infinity power. Okay, that's another indeterminate power form. Now, each of these 3 indeterminate forms can be treated using the natural logarithm and also L'Hopital's rule. There's a note here before we look at some examples. Infinity to the 0 power is an indeterminate form, but 0 to the infinity is not an indeterminate form. Okay, so be careful about that. You know, there is an arrangement of the items here. Okay, let's take a look at an example. Suppose we have the limit as x approaches infinity of 1 plus 1 over x to the x power. I've got a function to a power that is also a function. And, well, let's see. The limit as x approaches infinity of 1 over x, that's 0. So I'm looking at this third type here, 1 to the infinity power. That's an indeterminate power form. And so I'd want to be using the natural logarithm here along with L'Hopital's rule. Now the first thing I'm going to do is I'm going to call this limit y. Okay, if I find y, I'll have my answer. In this equation, I'm going to go ahead and take the ln of both sides. The ln of the limit of an expression is the same as the limit of the ln of the expression. In other words, the ln notation can come inside the limit. There's no problem with that. And of course, one reason for using logarithms is I can use my laws of logarithms here. I know powers can come out of logarithms, so I'll go ahead and pull the power of x in front. And okay, the limit as x approaches infinity of 1 over x, that's 0. ln of 1 is 0. Infinity times 0, well, 0 times any number is 0, but infinity is not a number. Okay, so I wouldn't just conclude that the result is 0. If I did that, I'd get a wrong answer. There is some work to do. Okay, so let me rewrite this as a quotient. X is the same as 1 divided by 1 over x. And am I in indeterminate form now? Well, the limit as x approaches infinity of 1 over x, that's 0. ln of 1 is 0. Yeah, so I'm in the form 0 over 0, right, indeterminate form there. So I can use L'Hopital's rule, and that's what I've done on the next line here. You got the limit as x approaches infinity of the derivative of the denominator would be negative 1 over x squared. The derivative of the numerator, that'd be a chain rule. Okay, the derivative of the ln of an expression is 1 over the expression times the derivative of the expression. The derivative of 1 plus 1 over x is negative 1 over x squared. The negative 1 over x squareds will cancel, and that would leave me with 1 divided by 1 plus 1 over x inside this limit. And the limit as x approaches infinity of 1 over x, that's 0. Limit of a constant is always the constant, so we get 1 divided by 1 is 1. Okay, now 1 is not my answer, right? Because I need to find y, where we found the ln of y, that's 1. Well, if the ln of y is 1, and we take e of both sides, e to the ln of y, that would be y. E to the first is e. So the value of this limit would be e. Okay, now this is a limit that you'd actually want to know. It does come up for some other things later down the road in calculus. And this is actually one way to define the number e. I had mentioned back in chapter 2 that there are several different ways that you can describe the number e. Okay, I mean, of course we already know the number e from algebra, right? But there's so many different applications of e and so many ways to describe this number, and you'll see that throughout calculus. So this is one way that you can describe e. E is a particular limit. Okay. Let's take a look at one more example. You got the limit as x approaches 0 from the right of sine x to the x power. Okay, well, sine of 0 is 0, so I'm in an indeterminate power form that is 0 to the 0 power, which means that I'll want to consider using natural logarithms in the calculation along with L'Hopital's rule. This problem is going to be very similar to the last one that we did. Let's call this limit y, and we got to find y. Well, I'm going to take the ln of both sides. By the way, the only reason why I've got direction indicated here, we're approaching 0 from the right, is because I'm going to be doing things with logarithms. Of course, the logarithmic notation can come inside the limit, and that allows you to pull the power in front of the logarithm there, inside the limit. Now, sine of 0 is 0. The ln of 0, that's undefined, right? The limit as x approaches 0 from the right of the ln of x, that's negative infinity. Okay, we've already looked at that. 0 times any number is 0, but I wouldn't have a number here, right, if it's negative infinity. So there would be some work to do. Let me rewrite this as a quotient. X is the same as 1 divided by 1 over x. And am I in indeterminate form here, so I can apply L'Hopital's rule? Well, the limit as x approaches infinity of 1 over x, the limit as x approaches 0 from the right of 1 over x, that would be infinity, right? If I'm on the right side of 0 there, the y values are increasing with the bound. Sine of 0 is 0. The ln of x, if you're approaching 0 from the right, would be negative infinity. So yeah, you're in indeterminate form here, negative infinity over infinity, and you can use L'Hopital's rule then. So I've done that. You got the limit as x approaches 0 from the right. The derivative of the bottom would be negative 1 over x squared. The derivative of the ln of sine x would be 1 over sine x times the derivative of sine x, that's cosine x. Cosine x over sine x is cotangent x. And, okay, I'm going to go ahead and flip the denominator, so I've got a negative x squared there in the numerator. Cotangent x, that's the same as 1 over tangent x. And the only reason why I've written it this way is so that we can see that we are still in indeterminate form. Tangent of 0 is 0. So I can apply L'Hopital's rule again. Okay, and I've got that here. We got the limit as x approaches 0 from the right of the derivative of the top, that'd be negative 2x. The derivative down under, that'd be secant squared x. And now there's no problem with plugging in 0. Okay, secant of 0 is 1. You're going to have 0 over 1 is 0. Now 0 is not my answer. Okay, the ln of y is 0. We need to find y. Well, if we take e of both sides, e to the ln of y is y, and e to the 0 is 1. Okay, so the value of this limit then would be 1. In general, whenever you have a limit and you have a function to the power that is also a function, and you can't make a direct substitution, this is going to be your option that you'd want to consider. You're going to use logarithmic differentiation along with L'Hopital's rule. Okay. The homework is on page 311. Be sure to look at the odd numbered problems that are listed there for me.